with that, I'd like to introduce Drew Wingard from Sonics.
Thank you very much. Can you guys hear me? It's okay? If I eat it, it'll be better? Okay. Is it tasty? Okay, yeah, so I'm Drew. I'm a co-founder and chief technical officer of Sonics. Sonics is best known as a company that works on chip networks. But last month we introduced a new line for us, which we call Ice Grain. It's focused on dynamic power management. I hope I don't have to motivate you that power is important. Whether we're working on battery-powered devices that go into our pockets, whether we're working on reducing the energy footprint in big data centers, where people like Google say that the cooling bill for their data centers is costs more than the servers that they're cooling. Whether we're worrying about regulatory requirements like Energy Star, or the equivalents in Europe that say how little power we're allowed to draw in standby mode for consumer electronics equipments, or whether we're building thumb drive sized set-top boxes that have to live in a box with no fan and still do incredible processing. Minimizing power energy dissipation is really important. So this is a slide from ISQED in 2009 that did an analysis based upon a bunch of other work of where are the biggest opportunities to save power. There's a lot of things we can do in process technology at the level of layout. There's things we can do in structuring our standard cell libraries and mapping onto them. There's things like fine-grained clock gating that we can do in logic synthesis. But the biggest opportunities for power are at the level of the architecture. And that's because at the level of the architecture, we have the best sense for what the application is trying to do with the hardware. We can make trade-offs. One class of trade-off that people talk a lot about is doing things wide and slow, just in time, versus doing things very, very fast and then turning things off to save leakage power, right? That's a good architectural technique. In this talk, we're going to talk about a set of techniques that are available to the integrator of IP cores. Now, we'll start at the top with something like clock gating, which can be done in a number of different ways. The push button thing that comes out of the logic synthesis tool today is fine-grained clock gating. It happens in a combinatorial fashion. It happens in the same cycle that the signals are happening, so it happens very, very quickly. If I work all the way down, I get to techniques like adaptive voltage and frequency scaling, which can take milliseconds to trigger. Well, why would I put this slide up? I want you to pay attention to this column, the transition latency. The difference in the amount of time it takes to go from the high power state to the low power state with fine-grained clock gating is less than a clock cycle. Down here, it's more like a millisecond. That's 6 decimal orders of magnitude of difference. It's pretty unusual, at least to me as an engineer, that when I'm trying to make a design trade-off, I have to trade off between something that has a factor of 1 million in it based upon making the right choice. So if I go to here, I can save the most power, but it may take me a millisecond to get there or to get back. Whereas this, I don't save as much power, but I can do it very, very quickly. So in the domain of dynamic power control, which is what we're going to talk about today, one of the things we have to worry a lot about is how long does it take us to get into and out of that low power state? And based upon that, what's the appropriate techniques to pick? A popular approach for reducing the power in a circuit, which reduces both dynamic power as well as leakage power, of course, is to shut it off completely. This diagram demonstrates what we call a power sequence diagram. It demonstrates the steps required to take something from a full shutdown where the external power management IC or the internal voltage regulator has been turned off to bring it all the way back to active. And you'll see there's a set of phases, which are these colored bands. I have to enable the voltage regulator. I have to turn on any power gates. I have to enable clocks and allow them to propagate to the circuit. I got to wait for the phase lock loop to get to the right frequency and a bunch of things like that. Typically, traditionally, these control steps happen in software. Today I'm going to talk about doing it in hardware instead. One of the reasons we don't like to do it in software is there's analog delays in these. A voltage regulator doesn't instantaneously produce the voltage you want. You have to wait for it to settle. When I'm going to turn back on my power gates and charge the internal nodes of the circuit, it takes some time to do it. So I end up having some delays in there. Microprocessors don't wait very well. Typically, when a microprocessor is going to wait, you end up returning from the interrupt you're handling, and you go do something else. And then when the settling time completes, you take a new interrupt to go do the next step. If you look at this sequence, you'll find that there are 7 places where the CPU would have to go do something else. And that means the minimum time through this algorithm, if you were going to do it in software, is 8 interrupt response times. Well, with a modern microcontroller dedicated solely to power management tasks, that's about 30 to 40 microseconds worth of time just in the overhead of the interrupts that you're taking. Now, actually, with a modern operating system like Linux, we don't take power management interrupts anymore. They happen too frequently. And so what we actually do is we gang up our power management operations behind the OS timer ticks, which themselves happen only every 30 microseconds. So to go through this sequence in Linux is 240 microseconds, or about a quarter of a millisecond, kind of best case. As you see, these steps are not that complex into and of themselves. They're actually very amenable to doing in a hardware state machine. And that's what we're going to talk about today. But one last thing I want to say about this is, who has seen one of these diagrams before? Anybody? You know why you probably haven't seen one before, even though you may well have worked on chips that do this? It's because when we build hardware, we don't think about the problem this way. We have a team of engineers who worry about the interface to the voltage regulators. We have a team of people who worry about the power switches and the isolation cells. We have a team of people who worry about the clocks. Okay? We think about this as a set of horizontal tasks which are going to be stitched together in software. It turns out that's a problem because that makes the verification much more difficult. By failing to identify this, we actually make the system look more general purpose than it's really going to be in practice, and we make the interactions from a verification perspective much more difficult to do. A couple weeks ago, we introduced something we call iScreen. iScreen is an architecture for minimizing power through the use of hardware to dynamically control power. It's a power subsystem. What's my definition of a subsystem? My definition of a subsystem is something that includes hardware IP together with the software device drivers, the software, to make that driver work inside a system. The goal of iScreen is to manage clocks, manage power supplies, manage techniques like dynamic voltage and frequency scaling, and other techniques in a single, uniform, easy-to-use, unified solution. It has to be safe, which means it's going to be done in a correct by construction, automatically verified way that doesn't have any of the power management deadlocks, which we actually see. Maybe you've never heard of a power management deadlock before, but there's plenty of examples of a chip in which this domain is ready to be turned back on, but he can't be because the signal that tells him to turn back on goes through some other domain that's currently off. If you're not careful, you do that one more way, you end up with an actual deadlock, and the only way out of that is a full hardware reset of the whole system. Additionally, iScreen implements detailed facilities for debugging. Why do we need to debug these power management systems? Well, one of the challenges in dynamic power control is that we have to detect when is the circuit idle, what power management technique to use when it's idle. And the right technique is based upon how long is it going to be idle. If it's not idle long enough, then I spend more time in transitioning than I actually spend in the down state, and so I waste power. So the debug facilities help you make sure that you're not thrashing from a power management perspective. But iScreen is intended to help you save power in 3 ways. One is by allowing you to build a larger number of smaller power domains, which we're going to call grains. I'll explain that in just a second. Second, we're going to make our power transitions in hardware so they're much faster than the software examples I just gave you. And third, we're going to do something a little bit crazy, which is we're going to take advantage of the fact that our hardware is so responsive that we can turn things back on fast enough that it's safe to turn them off without telling the software and the device drivers. So we're going to allow the hardware to take the parts of the chip to a lower power state than the OS and the drivers know about. So why do we call this iScreen? Well, I'm going to define a term, a power grain. What's a power grain? A power grain is a collection of logic that can be power managed. Now that power management technique might just be coarse grain clock gating. It might be switching it to a retention supply. It might be power gating it. It might be taking the voltage away. All those are an abstraction of different power management techniques. We want to help you identify collections of logic that want to be power managed. We're going to call those a power grain. Power grains can be hierarchical. So you might imagine a clock-controlled grain that lives inside a switched power grain, and several of those live within a voltage grain. Okay? We want to think about those because they help us structure and understand the control dependencies between the grains. The term ICE stands for, well, it's cold, but it stands for the instant control of energy, and that's simply saying that we're going to do this in hardware. By doing it in hardware, we can do it faster, and we can make power state transitions as independent from each other as we can. Because if I build a chip that has 100 grains, I don't want to have to wait. Just because your grain's going on doesn't mean that his can't turn on, right? I don't want to have them interact with each other. I want to make this very distributed and parallel. So when we look at how the hardware would be built, for each grain, there's a local grain controller that's floor planned. Not in the middle, please, but just at the end, please. Thank you. So for each grain, there's a local grain controller that's partitioned together with the logic it's controlling and is responsible for managing the power state transitions. Now, there's some resources which are shared. I have a limited number of voltage regulators. I have a limited number of phase lock loops. The shared logic is in the central controller. The central controller is also responsible, of course, for the interface to software. So the device drivers we're going to be providing, take the requirements from the OS and maps them into commands to this hardware. The interaction between grains, I mentioned that they might be hierarchical, come in the form of event signals which come back through this hardware interface. Okay. A key requirement of this architecture is we not put in place any burden on the host processor. So there's no fundamental latency reactiveness requirements on the host processor. We really are making these power state transitions in hardware. Okay, so here's a design. Here's a description of a conventional design, maybe broken up into 4 domains, and another chip with a set of domains. Now, if you guys would run the animation for me. Here you see how we can very quickly shut off some of these pieces. Now, only once this block over here goes all the way off could this guy in the companion design go, right? Because I can't shut something down unless everything within it is able to go down. What you'll see in just a second is I'm going to have most of this grain here, of these grains here, off, but this one's not, so I can't shut this one off, okay? So that kind of gives you a sense for how much more reactive we can be by using a larger number of smaller domains with hardware control over it. If you hit escape now, please, we should be able to get there. Thank you so much. Okay, so how much faster can we get? Well, here we're going to compare the hardware and software approaches. So in a software approach, in order to try to harvest some power, I have to wake up a processor and go through some number of these interrupt response cycles to get it done. Well, of course, the CPU takes a lot of power when he's operating, and if it takes a long time to do it, this box here represents the energy I spent getting to that lower power state. And what you see here is between the turn off and turn on transition, I've spent a lot more energy than I saved. This would be an example of thrashing. I've wasted energy trying to go to this lower power state. With ice grain, we're going to use hardware state machines, which use a lot less power, right, to make our power transitions, and we're going to do it over a much lower period of time. So all of this is energy that we can save in getting to low power state. We get to spend more time there, and then on the way back, we get done faster, turning back on, so in many cases we can actually finish our overall job more quickly. Okay, that's the idea. Now, how much faster? Well, early data from the work shows that when we compare against the best published data we've seen for transitions like going from a clock off standby, a retention voltage, or all the way from external voltage regulators shut down, the best numbers we see published for software control are numbers that are all multiples of 4 microseconds. Okay? What we've already got running today is hardware that makes these transitions much, much faster. Today what we're releasing is 10 to 20 times faster. okay? But I think the actual numbers are going to end up much, much better than that, okay? So that means that, this dimension of those boxes is much quicker. And what that means is you can take your block to a lower power state than you could have previously for a longer period of time, and that's how we're going to save you power. Okay, so how does this work with the operating system? So if you think about the device driver associated with the core, the OS sends that device driver command saying, hey, take your block from active to state S2. Okay, so abstractly from macro state X to macro state Y. What our driver will do then is take that command and say, okay, well, when I'm in state Y, there's a reactiveness expectation from the operating system. There's going to be a certain amount of time, a deadline I have to be able to meet to come out of that state and back to active. And so that's going to change the allowed set of microstates that each of the grains that make up that domain will do. In general, a hardware device will be broken into hardware that actually has multiple of these grains inside it. For some associated with the input circuits, maybe the reaction requirements is really fast. And for the processing circuits, which have some extra time, I can take them to a lower power state. And so the translation between those two is done by our drivers. Okay, so Sonix is understood, to be kind of a provider of networks. What's the relationship between iScreen and the on-chip network? Well, there is none, fundamentally. iScreen is completely independent from our other IP products, our on-chip networks and things, but there are some synergies that mean that they work very well together. One thing that's unique about our SGN product is that it is designed from the ground up to be able to span the boundaries of clock domains and voltage domains and power domains at any one of the internal links inside the network. Well, in capturing that design, you have to tell our design environment, okay, well, this component's on this clock and this VDD, and that one's on this clock and this VDD. That's the same information we need for describing the power domains to iScreen. Another thing is when we talk to customers about how do they do their power analysis, they say, well, we have a set of representative use cases that we do. Okay, well, we've heard that before because when they're configuring our on-chip networks, they have a set of representative use cases. Well, what's the overlap? Well, they say there's about 80% overlap. About 80% of the use cases that we use for configuring the network are identical to the ones that we'd use for determining the power domain boundaries. Well, that's a pretty good synergy. And then lastly, our on-chip networks have some extra bells and whistles around making design safe when you have a lot of clock and power domain boundaries. And that's particularly the ability that on the way into the network, this triangle, which we call the agent, knows the power state of all the other domains that the network's attached to. So you remember how I said that we were going to turn blocks off without telling the drivers? How do we know to turn things back on? Well, it turns out that because our network has the fundamental address decoders for the whole system in it, we're the first piece of hardware that knows when someone's trying to talk to something that's currently shut down. And so we have in the case of our network already the automatic signaling that says, let's say someone has just told the video encoder, go stream a new encoded stream to the SATA interface to the hard drive. And the SATA is off. Well, what happens is the agent associated with the video encoder is going to say, wait a minute, I can't send to him, he's off. So he'll send a message via his interface to iScreen that says, you better turn this guy back on. And once he has turned him back on, then the flow is allowed to go. So we can help do the equivalent of what the Wake on LAN facility that's in your laptop is what we call Wake on Demand, and we can do that because of the interactions between the network and iScreen. So that's pretty much the end of my presentation. I'll be glad to take some questions. If you want to know some more, we've got 2 other places where you can come talk to us. We're just over there in the just kind of behind you, in the ARM connected community, just on the backside over there, and then we're over in the IP Constellations community as well. Thank you very much for your attention.
Any questions for Drew? Yes, sir.
So I understood you know when to wake up, right? But how do you know how deep a sleep to go into? Like, should I go into a state where I've just clock gated, or should I retention or full shutdown?
Right.
I mean, because they all have different wake up times.
You're absolutely correct. That's a great question. That's what I was trying to describe when I mentioned the interface to the operating system. So we're going to take advantage of the operating system power states A deeper OS power state means I can go to a deeper hardware power state. So we're going to associate with each of those power states a reaction time. And so as part of the driver mapping, we'll say, hey, you know, that in state S2, I can go this deep. Oh, in state S4, I can go all the way down to there. Okay? It's OS influenced. The OS doesn't know where I'm going. The OS has given me a license to optimize. Okay? So what I want the OS to give me is a deadline. And then I'll determine, based upon the characteristics of my grain, how deep can I go and still meet that deadline. Okay, so it's an abstraction, if you will.
Excuse me.
Hi. So in one of the slides you mentioned you don't want one piece of the subsystem to know from the other piece when it's switching off or on. How do you sort of handle power network glitches?
Excellent question. So we'll go back. Okay, fine. If I could get slide, I can't read the number. Back up. Or maybe it's that one. Thank you. You remember how I mentioned that all the communication between these things happens through here? And there's resources in there that are shared. Okay? So there are situations in which there are interactions that we can't avoid, right? Like, I don't get to turn off the external voltage regulator until all the grains that are dependent upon it are power gated. Similarly, to the extent that there's power gating restrictions, I can't pump an infinite amount of charge out of my true VDD, then I have to manage those inside the central controller. So there is a request grant interface essentially between the local grain controllers that make that safe. A great question.
Any other questions? Yeah, here.
Okay, I'm from Mawea, so my question is for the implementation. So you will introduce a lot of power switch isolation cell and also the controlling signal because you bring it to fine-grained structure. So is there any tool support this?
Absolutely. So let me talk about the fundamental idea. So the fundamental idea is, we've been working on this in the background for more than 5 years. We think now's the right time to start introducing it because we're very glad to see things like the IEEE 1801 UPF standard having been, well implemented. So we believe there's now a relatively stable physical implementation platform that we can target. And so the way we actually communicate to that platform is, of course, via UPF. So as part of the ice cream program, we will be authoring the top-level UPF file for the chip, because we're going to take control of that. Only by doing that will make sure that the configuration of the ice cream controllers is consistent with the power intent that's being provided to the rest of the system. Okay.
So for logic level, your tool will split it into the fine-grained power domain, right?
Yes.
And also isolation will be inserted. So as the implementation tool only take your lattice, take your UPF, they can move on.
So the actual isolation happens through directives in UPF, right? We don't actually have to, we used to have to, in our networks, we used to have to put in place the isolation cells, right? Now you just use UPF and it directs the tools to do it for you. So, but yes, that's our job. Our job is to structure the netlist so it just works with the synthesis flow and the rest of the implementation flow.
Okay. Since I think you have a lot of case. So by average, if we go with the fine-grained power structure, what is the overhead regarding to area?
So what I can tell you is we're being very, very careful about that. In the trade-off between total area and area in the always-on part of the chip, we're trying to optimize area or minimize area in the always-on part of the chip more than total area. We're not at this point, really, it's not a product yet, it's just an architecture announcement at this point, so we're not releasing the specific details, but I would encourage you to come talk to us, after the thing, and we can talk about our current results.